Now, if we try to locate, no, if we try to locate the value of negative 25, the pressure on this one, so to make it accurate, so we refer to the call it the thermophysical properties of refrigerant. Now, along the temperature, so we have here negative 26 and 24. So what we are looking for is the pressure at negative 25. So it is in between. So we try to interpolate this one, getting this the value. So by means of interpolating, so we may able to achieve a 0.152 PPA. Sorry, this is MPa for the pressure. So I'm gonna change this one to MPa. Okay, so changing that one, we are in the units of MPa. Now, looking back to our pH diagram, so we can write here the pressure is 0.152 MPa. The pressure intersection, no? If we're going to intersect negative 25, since we have the expansion, that will be a constant enthalpy. So we can draw the line here. So from 0.5 going down, so try to draw the line. So we have here the intersection of so this is now our 0.6. So this represents as negative 25 degrees Celsius. So looking the overview ng ating pH diagram, so we'll see, okay, then we're going to connect 6 to this point at this negative 28. So the boundary, the intersection of the saturation vapor. So we have drawn down the line intersecting the saturation vapor. So from 0.6 going to saturation vapor and going to 0.7 and 0.1. So that completes the cycle of our simple actual vapor compression system, which is based on the given data. So you will see, you will observe the difference from yung simple vapor compression cycle to the actual vapor compression cycles because of the losses in actual, no? So yun yung pinagkaiba nila ng ideal to actual. So this is based on actual refrigeration, which is yung data which is coming from an existing refrigeration system or vapor compression cycle, which is the data is being taken in actual. Next, we need to find the properties point by point. So let's start the properties of enthalpy. So let's start with 0.4. So that will be 30 degrees. Okay. So if you're going to look at the pH diagram, so that is 30 degrees is somewhere here, subcooling. So that is almost in terms of so it is almost outside the saturation liquid. So it is a purely liquid. So H4, that will be the HF at the 30 degrees Celsius. So we can check also yung table for these values. Now I have highlighted 30 degrees Celsius. So we have the corresponding enthalpy. So in liquid form, we have 341.76. So writing it down here para all the data are available. Now let's go to 0.5. Knowingly, basing doon sa natin, pH diagram, 0.5 and 0.6, we have a constant enthalpy from 5 to 6. So we can write it down as the enthalpy 5 is equal to your enthalpy 6. Now our enthalpy 6, so that we equal to your HF at 32 degrees Celsius. So referring here our diagram, so 32, 5 and 6 are equal enthalpy. So expansion bulb, we have constant enthalpy here. So we're using the 32 degrees Celsius. And also referring doon sa ating pH diagram, we have here a constant enthalpy from 5 to 6 at 32 degrees Celsius. So that will be the HF. So going to the properties of our table, in the table of thermophysical properties of refrigerant of ammonia for 32 degrees Celsius, so it falls here. Now at 32 we have the HF enthalpy, that will be kilojoule per kilogram. So we have the corresponding enthalpy of 351.45. So let's write it here for our data. That will be 351. So that will be the unit of, we have the unit of kilojoule per kilogram. Now looking at our 0.6, so that will be negative 18 degrees Celsius. So the enthalpy at negative 18 degrees Celsius with the corresponding pressure of your 0.7 at this part, so that is 132, 0.132 megapascal with the corresponding pressure, and the temperature is negative 18 degrees Celsius. Okay. And also let's try to plot also the properties here in our pH diagram. So we have also for 0.6, 5 and 6, so that is 351.45. so this will be kilojoule per kilogram for the enthalpy at that point. Now for 0.4, we have here the corresponding enthalpy, so that is somewhere touching here. So we have the value of 341.76 corresponding on this point. Okay, now so let's go to find out the at 0.7, the enthalpy at 0.7. So we have your H at 132 kPa and negative 18 degrees Celsius. So for the enthalpy of this one is the intersection on our pH diagram. So looking at in our pH diagram, now looking at our pH diagram, we have here 14 and 16, and this is your 15, 14 and 16. So we are here in between 14 and 15 hundreds. Okay, so we can assume this point is it's around 1445. We can assume that one, since this is 50 already. So this is now your units of kilojoule per kilogram. Now at 0.1, we have your enthalpy at 0.1, so that will be the H at 132 kPa and negative 8 degrees Celsius. So that will be the intersection. So let's go to our pH diagram. So you will notice here that will be that one. So let's draw a line traveling here. Okay, so I have drawn the line at this point, so we can say this is 1470. So this is our kilojoule per kilogram. Okay, so that will be 1470. So writing it down. So we need also the specific volume. So later on we'll be needing this one for computing the volume flow rate. So we have the specific volume at 132 and intersection at negative 8 degrees Celsius for 0.1. But what we have here is not a specific volume but a density. So we have the density line here. Okay, so we can check that one. So you will notice here we have it is in between 0.8 and 1, so we can assume this line, so we can say this is 0.9 for our density. So I change that one, that will be 0.9. So we have the units of kilogram per cubic meter. Now for the enthalpy at point 2, so that will be the enthalpy at 1352 kPa and the intersection between 120 degrees. So looking back at the pH diagram, so 120, okay, this one, so we can draw the line here to determine what will be the enthalpy at this point. So what is the enthalpy of the intersection? So 120 with the corresponding pressure of 352 megapascal. So this is in our pH diagram. So we have 16 and 18. This is our 17 in the middle. So we can say this is 1725. So that will be the units of kilojoule per kilogram for this point. So let's write it natin dito sa natin data. So this is 1725. So that will be kilojoule per kilogram. Now at point 3, so that will be the enthalpy intersection of 1352 kPa of pressure and 110 degrees Celsius. So looking at our pH diagram, so ang point na yan, that will be this one. Okay, so this is our 110 and with the corresponding 1.352 megapascal. So the line, let's draw the line to find out the value of this one. Okay, so you will notice it touches this dotted line, okay, which is equal to 17,000 or 1700, sorry. So that is 1,700 kilojoule per kilogram. So this line. Okay, so we have 1,700 now. Looking back doon sa schematic diagram natin. Okay, so let's check if we have already completed the data of enthalpies from point to point. So for point 4, we have checking that one, we have here. Okay, so it's okay. We have already going to check this one. And for point 5, okay, we have also the properties now. Then point 6, so they have equal, it's okay. And point 7, it's okay, we have also equals for point 7. And for we have this one, point 1. So for point 1, we have your enthalpy, okay, it's okay. Then for point 2, we have now the enthalpy at the discharge line of our compression. After compression, then at point 3 before the condenser, okay, so we have already the enthalpy. Okay, so we are good to go to calculate the requirements needed in the problem.